Okay, so we are in the middle of the 2009 AB questions. We'll have 3 more to get through today. If we're able to get through all of them, we'll check the study guide and then stop there. So this could be a short session, but we'll finish as much as we can. So question 3, this is without a calculator, I believe. Double check that. I believe so. Okay. So question 3. The Mighty Cable Company manufactures cable that sells for $120 per meter. For a cable of fixed length, the cost of producing a portion of cable varies with its distance from the beginning of the cable. Mighty reports that the cost to produce a portion of the cable that is x meters from the beginning of the cable is 6 root x dollars per meter. First, we want to find the profit on the sale of a 25 meter cable. Okay, so to start off, our profit, get rid of my keyboard here. Okay, my profit should be equal to my money coming in minus my money going out. So my profit is the money that the company receives. I'm going to call that money in minus the cost of producing the cable. Or actually, let's call this revenue. Revenue or money in minus cost. So if we are selling $120 per meter and we sell a 25 meter cable, then my revenue is going to be 120 times 25. So that's the $120 per meter times the number of meters that we have. Okay, minus our cost. My cost is 6 root x dollars per meter. So I'm going to subtract what happens if we have a cable that runs from 0 to 25 meters. Should be equal to my profit. Okay, any questions on the setup?
No.
All right. So then we just need to go do this integral. Okay, I could say that 6 root x is the same as 6 times x to the 1/2 power. And then I could multiply this out. I think I'm going to leave this just like this for now, because I'm going to have to plug in a 25 at some point, and that might end up canceling. What's going to happen if I integrate 6 times x to the 1/2 power?
It's going to be 6x.
Okay, so I'm going to add 1 to the power and then divide by the new power. So if I add 1 to the power, we'll have x to the 3/2 power. And then what happens if I divide by the new power?
Well done.
If I'm dividing by 3 over 2, I'm doing the same thing as multiplying by what?
2 over 3.
2 over 3. Okay, then I'll have to plug in my upper bound and lower bound for that one. Okay. So we'll go ahead and multiply this out. I've got 120 times 25. Should give me, what is that? That's 3,000. Minus my 6 and my 3 will cancel, so I have 2 times 2 is 4 x to the 3/2 power. And then I've got to plug in my upper bound and lower bound for that part. Okay, if I plug in my 25 right now, I'll take the square root of 25 to get 5, and then cube it to get 125. So I have 4 times 125. I'll write it out. 4 times 125 minus 4 times 0 should give me 3,000 minus 500 is 2,500. And this is profits. This is $2,500. Any questions on what we did for part A?
No. Ms. Ryan, did you use calculator for the second last part?
Second to last part for here.
The integral?
I did not use a calculator for the integral, no. But if I plug in 25 into that 3/2 power and then multiply by 4, for the 25, if I take the square root, that's over 2, that'll become 4 times 5 to the 3rd power.
Oh.
And then if I cube 5, I'll get 4 times 125. 4 times 125 is 500. So 3,000 minus 500 is 2,500.
Okay.
Okay, good questions. So then I need to explain the meaning of the integral from 25 to 30 of 6 root x dx using correct units in the context of the problem. So 6 root x is how much it costs the company to produce a portion of the cable that is x meters from the beginning. So if I integrate from 25 to 30, this will be the additional cost of producing a 30 meter cable versus producing a 25 meter cable. So this is the additional cost in dollars to the company of producing a 30 meter 30 meter cable instead of a 25 meter cable. Any questions on that one?
No. No.
Okay. For part C, I want to write a general expression involving an integral that represents our profit on the sale of a cable that is any length long. What do you guys think I should do?
Integral.
Okay, I'm going to have an integral. Let me go ahead and write my general form for profit here. My profit is equal to my revenue minus my cost. So first, what will my revenue be if we have a cable of any length?
120 times K.
Perfect. Okay, 120K is how much money the company will take in. Then I'll have to subtract my costs, which is based on an integral. So what would my integral be?
Integral of 6 root x.
I'm going to integrate 6 root x from what to what?
From 25 to 0.
Not 25 to 0, no. That would tell me just to a length of 25. I want to go to a length of k.
K to 0.
Okay, from 0 to k. Okay, it's okay that this part is in terms of x, because when I plug in k for my upper bound, this will become k. So our general form is our profit is equal to 120k minus 0 to k of 6 root x dx. What are my units?
Dollars.
Dollars.
Dollars per meter.
Actually, just dollars.
Just dollars, yeah.
Okay. 6 root k was in dollars per meter, but we've integrated it in terms of our length. So now I just have dollars left. Any questions on part C?
Nope.
No.
Okay. For part D, I want to find the maximum profit that Mighty could earn on the sale of a single cable, and then justify our answer. Okay. So we're going to have to maximize this profit equation that we just created. So I'm going to start there. Our profit is equal to 120k minus the integral from 0 to k of 6 root x dx. Okay, to maximize a function, what do I have to do?
Derive.
I've got to derive it first, so we'll get our derivative of profit. Our derivative of profit is equal to 120 minus, what happens if I derive this integral?
First 6x.
Okay, so if I integrated this, I would step up and then plug in my upper bound minus my lower bound. When I derive, I would step back down to get back to 6 root x. But because I plugged in my upper bound initially, I would get 6 root k times the derivative of k, which is 1, minus 6 root 0 times the derivative of 0, which is 0. So this will give me 6 root k after I derive. So now I've got an equation for our derivative of profit. What do I do with this to find the maximum profit?
Equal to 0.
I'm going to set it equal to 0 to find the critical points. So 0 is equal to 120 minus 6 root k. I'm going to throw this 6 root k over to the other side, so 6 root k equals 120. And divide both sides by 6. The square root of k is equal to 20. So then k is equal to what happens if I square both sides, which is 400. Okay, 400 is the only critical point. I do need to check this critical point and make sure that we're actually changing from a positive slope to a negative slope. I could also do a second derivative test where you derive this to see am I concave down, because for a maximum my slope should be 0. My slope should change from a positive slope to a negative slope at that point, and I have to be concave down. If we know the slope is 0 when we're concave down, that's enough to prove that this is the maximum. I think I'm going to do a second derivative test for this, because I know that if I derive this, I'll get a negative answer. So I could say the second derivative of profit when k is 400 is equal to negative 6 times 20, or negative 120. Okay, so we can conclude the maximum profit occurs when the cable sold is 400 meters long. And I do need to find the maximum profit, so I actually need that value. So to find that value, I'm going to plug in 400 into our profit equation. So we'll find our profit when k is 400 is 120 times 400 minus the integral from 0 to 400 of 6 root x dx. Okay, we've already integrated this part once for part A. When I integrated, I got 6 times 2/3 was 4 times x to the 3/2 power. Okay, so I'll do that here. This is 4x to the 3/2 power from 0 to 400. And I'm going to subtract all of that from 120 times 400, which will give me 48,000. Okay, so I'll plug in my upper bound and subtract my lower bound. When I plug in my lower bound for 0, I get 0, so I only need to plug in my upper bound. So this is 48,000 minus 4 times 400 to the 3/2 power. I'll work this out completely this time. So if I'm raising something to the 3/2 power, that means I am taking the square root of what I have inside, and then I'm cubing it. So if I take the square root of 400, I get 20. So this is 48,000 minus 4 times 20 cubed. So that'll be 20 times 20 times 20. 20 times 20 is 400. 400 times 20 is 8,000. So I have 48,000 minus 4 times 8,000. Or 48,000 minus 32,000. Is equal to $16,000. Okay, so this is my profit at the length of cable that maximizes our profits. This is the most amount of money that the company could make on one sale. Any questions on anything that we did?
Nope.
No.
Okay. Moving on then. Okay, question 4 is an area volume one. We seem to be pretty good at these. We'll give this a shot. I've got region R, which is in the first quadrant, enclosed by the graphs of y equals 2x and y equals x squared here. First thing I want to do is find the area of R. So let's jump over to... I'm going to start with Sam. How can I find the area of this region?
Upper bound minus bottom bound.
Okay, so I'm going to integrate our...
Like integrate, yeah. Integrate from 0 to 2.
Okay, integrate from 0 to 2.
2 pi, pi.
I'm just getting the area.
So we don't need pi.
Don't need pi, I just need my top and bottom function. So which function is on top?
Top would be 2x.
2x. Okay, so I need top function minus bottom function, so that'll give me what?
2x minus x squared.
Perfect.
Yeah.
Okay. So I just need to integrate this then. Hongyan, if I integrate 2x, what will I get?
2x by 2 x squared.
X squared. Nathan, if I integrate x squared, what will I get?
1 over 3 x cubed.
X cubed over 3. Okay, so I'm going from 0 to 2, so I'll plug in 2 first. When I plug in 2, I'll get 4 minus 8/3. And then when I plug in 0, I'll get 0. So this will be 4 minus 8/3 minus 0. Or 12 thirds minus 8 thirds is 4 thirds. Any questions on our area?
No.
Nope.
No.
All right. Next one, I want to find an equation for a volume. This time, R is going to be the base of a solid. For this solid, at each x, the cross-section perpendicular to the x-axis has an area of sine pi halves x. I want to find the volume. So I'm taking cross-sections that are perpendicular to this x-axis. So we're going to have some shape that pops out of the page. We don't know what that shape is. So I'm drawing a rectangle, but we don't actually know that this is a rectangle. We just know that the area of this shape that is popping out of the page perpendicular to the x-axis will give me this area. In general, how do I find a volume?
Using disco geometry.
I want to go way more general than that. So if I wanted to find the volume of, let's say,
Width.
a box, how do I find the
Width.
volume of a box?
Width times length times height.
Okay, you did base times length times height. So you had a 2D area of your box that was a base times a width, and then you multiplied by a height. How do you find the volume of a cylinder?
You 1/3 pi squared.
That's a cone. So 1/3 pi r squared h. If, if you have a right cylinder, how can I find the volume?
Pi r squared times
Times the height.
height.
Times the height. Okay, for the box I had base times width, that was my rectangle, times height. For the cylinder I had pi r squared, that was the area of my circle, times height. So anytime you have a 2D area, you can multiply your 2D area times height to get the volume of your right shape. Okay, I'm going to do the same thing here. Our volume is equal to our area times height. So our volume should be equal to the integral of our area, which is the sine of pi halves x, times our height. Now my height is going to be my infinitely small part here that we've drawn outside of our curves. So you can think of it as the depth of this box that we've drawn should be dx. We're going to take that infinitely small height as I integrate this from x equals 0 to x equals 2. Will allow us to finish this off. So we'll cover all of the area between the two curves with cross sections that are perpendicular to the x-axis. Any questions on our setup?
No.
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 Okay, then we just need to integrate this. What happens if I integrate the sine of pi halves x?
Negative cosine times pi over 2.
So this is negative cosine of pi over 2x. We're not multiplying, I'm plugging this in. When I derive, I would multiply by whatever this constant is. So when I integrate, what do you think that I will do?
Times 2
Close.
times
Okay, when I derive the sine of pi over 2x, I would get the cosine of pi over 2x times pi over 2, right? So I had to multiply by the derivative of the inside with chain rule. If you integrate, I'll have to do the opposite. So if I integrate... Microphone muted. Okay, can you hear me?
Yes.
If I integrate, instead of multiplying by the derivative of the inside, you'll have to divide by the derivative of the inside. So if I derive the inside, I get pi over 2. I'm going to have to divide this by pi over 2 because of chain rule. Okay, and then my bounds are from 0 to 2. So if we are dividing by a fraction, we can flip and multiply. So that will give us negative 2 over pi times the cosine of pi over 2 times 2 minus negative 2 over pi times the cosine of pi over 2 times 0. Okay. What is the cosine of pi over 2 times 2?
2.
Okay, this is going to be the cosine of pi over 2 times 2 is the cosine at pi. What is the cosine at pi?
One.
Not 1, no.
0.
Not 0?
-1.
Negative 1. Okay, so my cosine at pi is negative 1. I'm going to erase these marks I just made. Okay, so I'm going to replace this cosine of pi over 2 times 2 with the cosine of pi, which is negative 1. Okay, minus... what's the cosine at 0?
1.
Okay, cosine at 0 is 1. So I have negative times a negative is a positive, so this is 2 over pi. A negative times a negative is another positive, plus 2 over pi. Should be equal to what?
4 over pi.
4 over pi. Okay, any questions on part B? Zoom out so we
Nope.
can see the question. All right,
No.
part C. I'm going to copy our question over again. Okay. So for part C, we're told that another solid has this same base r, but for this solid, the cross-sections perpendicular to the y-axis are squares. I want to write an integral expression for the volume of this solid. So cross-sections perpendicular to the y-axis are squares. So if I popped this out of the page, I would get the shape of a square. Each one of these squares has an infinitely small change in x side. That is the width of these squares. Okay, so it looks something like this. I've got this part is my change in x. This part and this part on the base are both the same value because this is a square. Those values are my changes in the x value of my two functions. So this is x2 minus x1, and this is also x2 minus x1. Okay. So what should my total volume be then?
Um,
Integrate from 0 to 4.
Okay, we'll end up integrating from 0 to 4 because this will end up being in terms of y. So this is how much my y value changed. I'm integrating in terms of y because I'm going to have to solve these variables for x. I actually wrote dx here, so this should be dy. We've got a change in y should be how much our base changed here. Okay, so if I'm integrating in terms of y of x2 minus x1, I need to know what x2 and x1 are. So I'm going to take both of these y values and solve for x. Okay, starting with this one. If y is equal to 2x, so that's my innermost function. This is x1. What is x1?
1 over 2x.
Okay, 1 over 2 y. And then y is also equal to x squared. That's x2 because that's my one that's furthest out. If I wanted to solve for x sub 2, what would x sub 2 be equal to?
Root y.
Root y. Okay, so then I'm just going to resub in here. Therefore, my volume is equal to the integral from 0 to 4 of x2, that's the square root of y, minus x1, y over 2, dy. Okay, it said write but do not evaluate an integral expression, so I believe we're done at that point. Any questions on what we did?
oh,
No.
Okay. Last one, then we'll take a look at the scoring guides for these. So we've already done question 5 yesterday.
Mr. Brandon.
Yes.
For the last question, shouldn't we also square the expression inside the integral?
Oh, you're right. I didn't do that, did I? We're creating a volume of a box. So I've got our squares. That's our base times height. So this should be squared. And after I substitute, that will stay squared. All right, thanks. Okay. Jumping down to the last one for question 6. Okay, for the last one, we have this derivative of our function is this piecewise function. Our derivative is g of x for x is greater than or equal to negative 4, but less than or equal to 0. And our derivative is 5 e to the negative x over 3 minus 3 after 0. Our continuous function of the derivative, we're not graphing f, is shown here. It has x-intercepts at negative 2 and at 3 natural log of 5/3. 3 ln 5/3 and negative 2. The graph of g between negative 4 and 0 is a semicircle, and we're told that f of 0 is 5. For the original function, though, not for this graph of our derivative. Okay. Any questions on the information they gave us first?
No.
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 Alright, again, the tricky thing is we are not graphing the original function, we're graphing f prime. Okay. So first thing, for all values between negative 4 and 4, I want to find all the values of x at which the graph of f has a point of inflection. If I'm looking for a point of inflection, what am I looking for?
the top or the maximum or minimum of the graph.
Okay, so a maximum or minimum of our original graph would be a critical point. Point of inflection is based on our second derivative. So a point of inflection is whenever our second derivative changes sign. This graph is our first derivative. So my second derivative would be the slope of this graph. So slope of graph is the second derivative of our original function. Are there any points you see where the slope of our graph of f prime changed from positive to negative or from negative to positive?
From negative to positive.
-2 to 0.
Which point? I'm looking for at what point did we change our slope from positive to negative or from negative to positive?
-2. And then 0.
Perfect. So at x equals -2, I could say f prime changes from decreasing to increasing. At x equals 0, f prime changes from increasing to decreasing. Okay. Therefore, f has points of inflection. At x equals 0 and x equals -2. Any questions on part A?
No.
No.
Okay.
No.
For part B, I want to find the original values of our function at x equals -4 and at x equals 4. So let me scroll down just a little bit and give us some space. We were told that f at 0 is 5. F at 0 is equal to 5. If f at 0 is 5, and I want to be able to get to f at -4, then I could say f at -4 is equal to my starting point, f at 0, plus the change from x equals 0 to x equals -4 of our derivative. Okay, this is a little bit tricky because my bounds are flipped, right? Usually we have a lower bound and then we go to an upper bound. Right now I'm having an upper bound and I'm going to a lower bound. So anytime we flip our bounds, we can swap our sign. So it looks something like this. F at -4 should be equal to f at 0 minus the integral from -4 to 0 of f prime of x dx. I've flipped the bounds, so now what was my upper bound is now my lower bound, so I'm moving from left to right now instead of from right to left. But I'll have to subtract instead of add. So this is changing the sign. Okay. We were told that f of 0 is 5. And then I'm going to copy our picture down. If we look at the picture, we should be able to get our area that's underneath that curve. Because we were told we were told that our shape here is a semicircle between -4 and 0. Okay, so taking a look at our picture really quick. If all of this shape forms a semicircle from x equals -4 to x equals 0. And I have a semicircle with a radius of 2. So how much is this area that I'm shading in red?
2 pi.
pi r.
Okay, I heard it somewhere. So this is, my area is pi r squared for a whole circle. I have half a circle, so this is 1/2 of pi r squared. If my radius is 2, then this is 1/2 of pi times 2 squared, which is 4. So this is 1/2 of 4 pi is 2 pi. Okay, I don't want this area in red, but I do want this area in white. Here, I'm going to draw with a different color. I want this area in, I'm going to make this green. So everything that is not inside our 2 pi is what we want. So I'm going to take the area of this entire box that I'm going to draw here in blue. And then we'll subtract the area of the red 2 pi, and that should give us the area of the green.
Mm.
Okay. What's my area of this box?
20.
Not 20? What's the area of the blue box?
-16.
Okay, so I've got 4 units down here from 0 to 4, and I've got 2 units here, right, from 0 to 2. So my area is,
-8.
okay, so I've got an area of 8. We're moving from -4 to 0, so this is still a distance of 4, and this is a distance of 2. Okay, so then I'm gonna take away 2 pi from my red space. Oops. Come on.
2 pi.
I'm going to take away the 2 pi that we have in red, and that should give me the area that we want in green. So our area is 8 minus 2 pi. Any questions how I got here?
No.
No.
Okay. So I'm going to zoom out, and we'll substitute that in. Our integral of our derivative from -4 to 0 was equal to 8 minus 2 pi. So that whole integral is 8 minus 2 pi. And then f at 0, we were told in the original problem, is 5. F at 0 is 5. So I have 5 minus 8 minus 2 pi should be equal to f of -4, or f of -4 is equal to 5 minus 8 is -3. Minus -2 pi is positive 2 pi. So I have 2 pi minus 3 is f of 4. Any questions on how we got f of -4?
Oh.
Okay, I was also asked to find f of 4, so I'm going to do almost the same process. So I'm going to have one of you guys walk me through it then. How do you think that I would find f of 4? Based on what we did last time.
Is this still f0 plus the integral from 0 to 4?
Perfect. Of f prime x dx.
Yes.
Okay, so I need the area underneath the curve from 0 to 4 of our derivative. So that's this part. Um, now we don't have a shape for this, but we do have a function for this that we can use. All of this area in the dark blue that I'm shading in now, from 0 to 4, I'm going to call A2, is equal to the integral of 5e to the negative x over 3 minus 3 from 0 to 4. Because I was given a function for it here. Okay, any questions on how we got the area here?
Nope.
No. No.
Okay, so let's go ahead and plug that in. So this is the integral from 0 to 4 of 5e to the negative x over 3 minus 3. Plus, we already know f of 0 is 5 from our problem again. So I'm going to pull that down. Okay, so now I just need to integrate this and we'll be set. Self a little bit more space again. And we're good. So what happens if I integrate 5e to the negative x over 3?
Negative 15 e to the negative x over 3 minus 3x.
Okay. From 0 to 4 before I forget. So if I'm deriving e to the u, I would get e to the u times du. So if I'm integrating e to the u, I'll get e to the u divided by du. If I divide by negative 1/3, that's the same thing as multiplying by negative 3. So I'll have 5 times negative 3 is negative 15 e to the negative x over 3 minus 3x. Any questions on that integral?
No.
No.
Okay. So I'm going to pull our line down and we'll finish this off. If I plug in 4, I'll have negative 15 times e to the negative 4/3 minus 12. And then subtract my lower bound, minus negative 15 e to the negative 0 power. Anything to the 0 power is 1.
One.
Yep. So that e to the 0 will become 1. 1 times negative 15 is negative 15. Okay. I don't think I can pull this down anymore. So if I simplify this, I'll get 5 plus negative 12 plus 15. So that'll be 8 minus 15 e to the negative 4/3 should be equal to f of 4. Any questions on what we did?
No.
No.
Okay. Last one. I'm going to go back and copy your picture one more time. Okay, last one says, for our values from negative 4 to 4, find the value at which f has an absolute maximum, and then justify the answer. So one more time, how do I find the absolute maximum of a function?
second derivative.
Okay, so I'm going to set the derivative equal to what?
0, right?
Set the derivative equal to 0. So I'll find any critical points. At what points is the derivative, so that's this graph, equal to 0?
At the point where at 0 and -2.
-2 we are equal to 0, but at 0 we are not equal to 0. This is the graph of f prime, so I'm looking for where is the y value of this graph equal to 0.
Is it 2?
Not 2, no.
Three ln 5/3
Perfect.
and -2.
We have x-intercepts at -2 and 3 ln 5/3, so that's right here. Okay. So if I want the absolute maximum, starting at where we were at -4, I added all of this y value that I'm shading in red to get my new y value at -2, and then I kept increasing after -2, so we kept adding all of these y values until I got to whatever my y value was when x was 3 ln 5/3. Then I started decreasing by this much area to get our last y value. So where should my maximum be, do you think?
Um, 3 ln 5/3.
Perfect. We have, I was going to write our function, but I'm going to write f. F has an absolute maximum at x equals 3 ln 5/3. Since f prime of x is greater than 0, on the interval from -4 to here, so 3 ln 5/3. Oops, actually that's not true, is it? At -2 it does become 0. I need to break this up. So from -4 to -2 not included. And from -2 to 3 ln 5/3 not included. Okay. And f prime at x is less than 0 on the interval from 3 ln 5/3 to x equals 4. Therefore, I actually already wrote the conclusion up here, so I don't have to rewrite it again. But therefore, f has an absolute maximum at x equals 3 ln 5/3. Any questions on part C?
It's,
Okay.
is it okay? Can you explain again?
Yeah. So this graph is the graph of f prime. And our graph of f prime was positive from x equals -4 to x equals 3 ln 5/3. So that means my original function was rising from x equals -4 all the way to x equals 3 ln 5/3. After 3 ln 5/3, it started to decrease because my f prime was negative, which means the slope of my original graph, f, was negative. So if our graph changed from increasing to decreasing at the point 3 ln 5/3, then this should be a maximum.
Okay.
Okay, I'm going to flash the scoring guides and we'll see how I did. Let's see, I think I'll start with the last one. Okay. So we got, for part A, 1 point for identifying x equals -2 or x equals 0 as the point of inflection, and then 1 point for having our answer with justification. We changed from increasing to decreasing at that point. So we were good for both of those points. We got 2 points for finding f of -4 to be 2 pi minus 3. That's perfect. So we had an integral, which is good, and a value. For f of 3, for 3 points, we had f of 4. We needed an integral, and they're set up the same way we did, which is good. The antiderivative, so what happened when we integrated, we should have got the -15 minus 3x is good. And 1 point for our value is good. Okay, so we're all 7 points so far. Last one was our answer with justification. Our answer was having an absolute maximum at 3 ln 5/3 is good, and then our justification, we changed from increasing from -4 to 3 ln 5/3 to decreasing afterwards. Okay, so all 9 points there. On the AP exam, usually your answers are only 1 point out of 9. So it's really important to show your work, and if they ask for a justification or explanation, to write a sentence. Any questions on this one?
No.
No.
Okay. I'm gonna flash the last two that we did today, but we're pretty much right on time right now. So the one before that, we had 1 point for our integrand, 1 point for the antiderivative, so that would be what happened after you integrated here, and then 1 point for your answer. So part B, same thing, integrand, what happens when you integrate it, and then what's your answer. And then last one, 2 points for your integrand, and then 1 point for your limits, that's 0 and 4. Any questions on how we're scored?
So
No.
No.
All right. Last one. 1 point for our integral for the profit. So that was our revenue minus the integral that we had for cost. And then 1 point for our answer of $2,500. 1 point for an answer with units. So I had an answer of... Okay, we're talking about the difference in cost of producing a 30 meter versus a 25 meter cable. We needed to use meters somewhere in there. I've got 1 point for our integral and 1 point for our expression. So your integral is just this right-hand side where we're looking at the cost, and then your expression is the whole thing, profit equals revenue minus cost. Then the last part, 1 part for setting the derivative of profit equal to 0, 1 part for getting 400 when you set it equal to 0, 1 point for your answer of $1,600, and then 1 point for your justification. Our P prime changed from positive to negative at that point, so it must be a maximum. Okay. Any last questions on anything from the tutoring sessions?
as long can we can use calculators for all these questions, right?
No. So all the ones we did today were without calculator. When you get your test, you guys will have a calculator on question 1 and question 2 for your free response. You will not have a calculator for questions 3, 4, 5, or 6. So the way it works is you will start out with no calculator on a multiple choice section. After your first section, they will give you a calculator for your second section, but take away your multiple choice for section 1. So you finish your last part of the multiple choice with a calculator. Then you start your free response with the calculator still on your desk. They take away your multiple choice. Then they leave your 2 free response that you had with a calculator, but take your calculator away, and you do the last 4 questions without a calculator. You can go back during those last 4 questions to answer stuff from the previous 2, but you don't have a calculator, so you won't be able to answer all of it. So if you didn't finish writing setups, you can go back and finish writing setups for your first 2 free response questions. Each individual free response question is 15 minutes long. So your with calculator section with the free response is 30 minutes because you only have 2 questions. And then you've got 60 minutes for the no calculator free response.
Okay.
Okay. Some of the older exams, if you go back far enough, don't have the exact same format. There were weird splits of different amounts of time with a calculator and without a calculator for previous years. But the way that it will work for you guys is 2 free response questions with a calculator, then 4 without. All right. Thank you guys so much for coming. I know I've taken a lot of your time over the New Year's, and I really appreciate you guys showing up.
Thank you.
Thank you.
Thank you.
See you guys later.
Bye.
Mr. Brendan.
Bye.